Hi and welcome to this video which I have been thinking of preparing uh, and it's connected with some of the questions we get at GCSE or even 11 plus about the angles between the hands of a moving clock, the angle between the minute hand and the hour hand. To demonstrate this, I have created here uh, a little animation of a clock which as you will see in a minute, the minute hand in this clock moves much faster than a normal clock. If I set the clock going, it's at 5 o'clock at the moment. So if I set it going, this is the minute hand moving, and we get a lot of questions. You may get to be asked about what are the angles between the minute hand and the hour hand at different times of the day, depending whether the clock is showing 6 o'clock. For example, we're coming to 6 o'clock here. At 6 o'clock, this angle is 180 degrees, for example. And as we're moving on, the question is quite often can be asked in two different ways. One way is what is the angle between the two hands of a clock at a particular given time? And the other question, which is slightly more difficult to tackle, is that at what time will the angle between the hands of a clock be a particular value? And this is the two types of questions I'm going to tackle in this video. So I'm going to stop the clock now and I'm going to bring it back to say 5 o'clock. Let's put the clock back at 5 o'clock and we can start examining what happens once the clock starts moving. Okay, first we're going to have a look at what happens to the angle between the two hands of a clock qualitatively, what is happening when the hands are moving, and then we will use the information that we will glean at in this video to make the necessary calculations. Now, I've set the clock to represent 6 o'clock. I think this is a bit easier to see that 6 o'clock. And the angle between the two hands is 180 degrees. Now, if I set the clock going, say I'll let it go for 10 minutes. There, we're going now 6:05. Okay, at 6:10. Now, what happens as the minute hand is moving, it is reducing the original angle of 180 degrees. It is reducing it. And as the clock is moving, the hour hand is increasing the angle. But the hour hand is moving much slower than the minute hand. This is why the net result is that the angle keeps getting smaller. Now, if I continue, you can see that this angle is getting smaller, but the hour hand is moving away from the vertical here, though increasing the angle. But the orange hand, which is the minute hand, is closing the angle. If I go back to the beginning, say at 6 o'clock. Okay, in this next session, I will eliminate the hour hand. As we can see, the minute hand is moving and is reducing that angle. Now, if I look at the block the minute hand and just let the hour hand move, see the hour hand is moving much slower. So the combination of the two means the angle is closing. Now, obviously, when the minute hand overtakes the hour hand, then this angle will be increasing. So depending on what the question asks, etc., we must be mindful of the fact that which angle we are talking about. And don't forget, there's always two angles when two lines cross. So one will be increasing, one will be decreasing. But the essential thing is to realize that if we start at any particular time, say if I start here and I look at the small angle between the two hands, as the minutes pass by, the minute hand is closing the angle, the hour hand is trying to increase the angle by a much smaller amount, which we will calculate in a minute. And as we cross, then the minute hand will be increasing the angle, and the hour hand will start to decrease it, but in a less, by a less amount. So when the minute hand is moving away from the hour hand, the net change in the angle is an increase, and when it's moving towards the hour hand, the net change is a decrease. For example, if we start at 7 o'clock, if we look at this angle here, as the minute hand moves, this angle will be decreasing because the minute hand is moving towards the hour hand. But this angle will be increasing because the minute hand will be moving away from the hour hand, as you can see demonstrated here. Okay, now that we've seen conceptually what happens when the clock is moving and what happens to the angles between the two hands, we can now use this information to make some calculations regarding the angles between the two hands of a clock. Okay, here we have a sample question. We are asked to find the angle between the minute hand and the hour hand of a clock at 10 minutes past 5. Now here I'm showing with the full lines a clock which is showing me 10 minutes past 5, and the dotted lines are the two hands at exactly 5 o'clock. Now at exactly 5 o'clock, the angle between the minute hand and the hour hand, which is this angle here, if I'm going to show you like that, that's about, well, it's not about, it's 150 degrees, because each graduation on a clock, it's 30 degrees, because it's 360 degrees all around the clock, and it's divided into 12 equal intervals. So 360 divided by 12 is equal to 30. So each graduation here is 30 degrees. Now, if I take that off, the other thing that we should notice that in 1 hour, the minute hand moves 360 degrees. That means in 60 minutes, it travels 360 degrees. So for every minute, the minute hand moves 360 divided by 60, which is 6 degrees. But for every hour, the hour hand only moves one graduation, goes from 12 to 1, or from 1 to 2, from 2 to 3. So it moves only 30 degrees. So for every minute, the hour hand will move 30 degrees divided by 60, which is 0.5 degree. means for every minute the R hand moves half a degree. And these two bits of information is what we will make use in all calculations of this type. So now we want to find out what is the angle between the two hands at 10 minutes past 5. Now, the dotted lines show where the hands were at exactly 5, and the full lines show where the hands are at 10 minutes past. If we look at the angles at 10 past 5, this angle has been reduced by this much, and this angle here between the two R hands that was and where it is now, that little angle here, that has increased. But because this increase is larger, there's a net decrease. Now, by how much does the minute hand increase the angle? The minute hand increases 6 degrees for every minute. So in 10 minutes, it will have moved 60 degrees. The R hand will have moved 10 times 0.55 degrees in 10 minutes. Now the R hand increases the angle and the minute hand decreases the angle. So for every minute, the net change is 5.5 degrees. So in 10 minutes, 10 times 5.5, the angle reduces by 55 minutes. But the original angle at 5 o'clock is 150 degrees because the big hand is on 12 and the R hand is at 5. So at 5 past 10, the angle would be 150 minus 55, which will be 95 degrees. Just to do a quick recap, at 5 o'clock, the R hand and the minute hand are as shown. The R hand is at 12 and the minute hand is at 12 and the R hand is at 5. This is the two dotted lines here. And the angle between them is 1, 2, 3, 4, 5 lots of 30 degrees, which is 150 degrees. At 10 minutes past 5, which is the two hands shown in full, the minute hand has moved 10 minutes, and for every minute it gains 6 degrees. So it has closed this angle by 60 degrees, but the R hand will have moved half a degree for every minute. So it will have moved 5 degrees to increase the angle. So the net change is always 5.5 degrees for every minute change in the angle. So in 10 minutes, then that angle has been reduced by 55 degrees, which means at 5 past 10, the angle between the two is going to be 95 degrees. Now for the second part, For the second part, we want to know at what time between 5 and 5:30 the angle between the two hands will be 73 degrees. Again, we're talking about the smaller angle between these two. Now, here we will use a little bit of algebra. We don't know how many minutes after 5 the angle between the hands will be 73 degrees. So we assume the number of minutes to be t. So t is the number of minutes after which the angle will have reduced to 73 degrees. Now we know that for every minute, the angle reduces by 5.5 degrees. So for t minutes, the angle would reduce by 5.5 times t degrees. I.e., for after 1 minute, the angle will reduce by 5.5 degrees. After 2 minutes, it will be 2 times 5.5, which would be 11, and so on. So we set up a little equation now. We want to, our equation would be this. 150 is our starting angle at exactly 5 o'clock. So we want to know 150 minus 5.5 t. This must equal to 73 degrees. That means after t minutes, and for every minute we take 5.5 degrees away from 150, after when will the angle be 73? This is a small, simple algebra equation. If I rearrange the terms, I'll get 150 minus 73 is equal to 5.5 t. This will be 77 is equal to 5.5 t, or we can say 5.5 t is equal to 77, which means t is equal to 77 divided by 5.5, which will be equal to 14. So that means at 14 minutes past 5, the angle between the big hand and the little hand will be 73 degrees. I hope this video has been educational, and the two things that you need to take with you and commit to memory is that, well, 3 things. That for every minute, the minute hand moves 6 degrees, the hour hand moves half a degree, and the combined total is either a 5.5 degree increase in the angle or decrease, depending on whether we're moving towards the hour hand or whether the minute hand is moving away from the hour hand. But obviously, every question you have to look at the setup and what is being asked. To do a quick recap, what we did here, we started at 5 o'clock, which are the dotted lines. At 5 o'clock, the angle between the two hands is 150 degrees. And we wanted to know after how long between 5 and 5:30 will the angle be 73 degrees. If we assume after t minutes, then we know that in t minutes, the angle will get reduced by 5.5 t. We set up this equation, 150 minus 5.5 t is equal to 73, which rearranging gives us 5.5 t is equal to 77. And the answer is 14 minutes. So at 14 minutes after 5, the angle between the two hands of the clock is 73 degrees. Please give this video a like, and if you like, subscribe so that you can see my other videos.